In this, we are going to learn one of the very important topic in mathematics called the local maximum and local minimum. This is also called the relative maximum and relative minimum in certain books. Relative maximum and relative minimum. So there are two types. There are two types. There are two types of maximum and minimum. So the first one is what we call the one that we're going to focus on this video is the local or the relative maximum and minimum. Then the other one is what we call the absolute or the global. The global or the absolute. Sometimes we call absolute. Absolute, a maximum and minimum. Okay, so in this video we're going to focus on mainly the local or relative maximum minimum, and in another video we're going to talk about the absolute maximum minimum. Absolute maximum minimum is easy to understand. So so let's focus on the local maximum and minimum. So local maximum and local minimum. I'll just call it minimum. Local maximum and minimum. So we assume that there's a function which is defined. So suppose f, the function f is defined on some interval I, on some interval I, on some interval I. So this interval can be open or closed or both. Because in one end it can be open, in the other end it can be closed. So so we can see so can be open, closed, or both. Both means one end can be open, one end, other end can be closed. So it cannot happen at the same time, but that's what it means. Okay, so let's look at a graph. It should be very clear if you look at a graph. So we can look at this graph. So the y value and the x value. So this is exaggeration. So the function. So go like that. So this is the interval going. So this interval is defined. So it may be open or closed. And then what we can see is that, so you can see that if you look at this point, I'm going to call this point is C. So what we can do is around this point C, this is a very important part, around this point C, we can have a small open interval. That open interval is entirely within the I interval. So you can find a small, very small open interval that is entirely inside the interval I, the bigger one. And then if you pick any point, in that small interval, very small interval, and you can see, so for example, so this value is what I'm going to call the FC value. You can see in this very small interval, if you look at this very small interval, so if you pick any point in this interval, you can see FC is the largest value. So if you can see, if you pick any other point, so I'm going to pick like any other point. For example, let's say this is the point. So I'm going to pick a point here, the x point. And you can see if you evaluate the function at that point, so you pick any point. This is just one example like that. And you can see that value is smaller than the FC value. So that is the value fx. You can see that FC is the largest, FC is the largest among all the values inside that small interval. The small interval is not I, that small, the red interval. So you can see if you pick any point in that interval, you can see FC is the largest. So if this is the case, we call this is a local maximum because it's happened only locally in that small region. So this is what we call the local maximum or the relative maximum because relative to that open interval. Good. So let's write the definition. So if you write the definition, so what it says, so let f be defined on some interval I. So there are no restrictions on I. It can be open, closed, or both. We say if has a local maximum, if has a local or relative maximum, FC, the value is FC, that's the maximum value. You have to find that FC value, relative maximum FC, if FC is greater than or equal fx for any value in that open interval, that the red open interval, for any x in some open interval. This will be open in some open interval, containing C that lies entirely in I, in I. So that small interval should be inside I. So that's the definition that makes the local or relative maximum. So what it says, let f be defined on some interval I. We say if it has a local maximum or local minimum. In this case, actually local maximum, or local minimum. Local maximum FC if FC is the largest value in that small interval for any x in some open interval. These words are very important. Open interval containing C that lies entirely in I. So that is the definition. So it's very easy. So what we normally do is, if you want to show that something is a local maximum, what we're going to do, we find an open interval, very small open interval that is inside that I, which is the domain of the function, and in that small open interval we see that FC is the largest value in that interval. So that's how we are going to show that. So that's that. So that way, if you look at the graph of this interval, so you can see this is the so that is the part of the graph we have, and in that part you can see if you accelerate, it's going to look like this. So that is the graph. That's the only open interval, and you can see that is that largest value we are talking about. So that is that small open interval which is on the x-axis. So that is that red interval here. So the I is like that's a bigger one. That's like I is like something bigger like that. Okay. So and this is the that value C. Good. Okay. So that's about the local maximum. So there are several other ways to say the same thing when we discuss this. So for example, so let's say other ways to say this. Other ways to say this. So for example, we sometimes say there is a, so this is another way to say it, there is a local maximum, FC at the point, you can say at the point CFX, CFC, you can say it like that. So that's like you clearly say what is the actual point on the graph. So C is the X value, FC is the Y value. So you can see this is the X value and that is the Y value. So we just give the XY coordinate. So the other way to say this one is, you can say there is a relative, sometimes it's a relative or local, you can pick one of the words, relative local maximum at, you can say X equals C, just give the X value, you can say just the X value. So last time we gave the whole coordinate, or sometimes we say the X value. So the other ways, we can also say there's a local maximum. So there is a local maximum, at CFC. That's another way to say it. So we don't say what is it, we just say there's a maximum at the point. And one more, we can say like FC, just the value, FC is a local maximum. So these are like several other ways to say the same thing. So now let's look at what we mean by a local minimum. So we're going to look at this graph. So in this graph, and you can see that the point, like let's say D. So this is the open interval, that this is the interval I, the domain. That's like a larger domain. And this is the graph y equal fx. So you can see D, so that means the corresponding y value is fd. Now what we're going to do, as before, we're going to look at a open interval around D, small open interval around D. And if you look at this interval, so I mean like just to like exaggerate, I'm going to pick a little larger interval like this. So that interval is entirely inside I. So you can do that. If you cannot do that, then we cannot, there's no local maximum minimum. Now we can see in this interval, if you pick any point in this interval, this is the corresponding function values. So the corresponding function values, and you can see if you pick any point in this interval, for example, I'm going to pick this value, so that's the x value in this interval. And if you look at this value, so this is the corresponding y value, so that is the fx value. And what happened, any point in this interval, for any point in this interval, you can see that if D is the smallest among all the values, all the other values in that, only in that interval. That's why we say locally, because it happened locally in that interval. So this is the case we call if D is the local minimum. So that is the minimum value that can happen. So it's a minimum. So there are some extreme cases that we can discuss later. So let's try the definition. So if has a local maximum, a local minimum, if has a local minimum, fd at x equals c, if fd is less than or equal fx for all x in some open interval containing d. That open interval should contain d, and that interval should lies entirely in I. So if we can do that, then we say if D is the local minimum, as a local minimum, because that happened locally inside that open interval. So if you cannot do that, then there's no local minimum. So we can discuss cases when it can happen and when it cannot happen. So let's look at some special cases now. So I'm going to give, we can talk over these few nodes. So let's say node. So you can say the endpoint, endpoints cannot be local maximum minimum, local or relative maximum or minimum, local maximum or minimum, both. Since it to be very clear when you graph it, since there is no open interval, since there is no open interval, since there is no open interval, that is entirely in I, and contains the endpoint. So it will be clear because that's the major part. It has to contain entirely in I. So let's look at the two cases. So let's see, we have a graph. So this is a closed end, and this so that's like the graph. So one is open, one is closed. So this side is open, here it is closed. So the problem is, you can see now, so the first one in the closed end, so if you try to consider an open interval, you can see part of the open interval is outside. So this part is outside. So that's why I say, so it's not entirely in the domain, because this is the I. So you can see I is only this part. That's the domain of the function. So you can see this part is out. So, and what happened on the other end, you can see that the point is not included, because this point is not there. So then we don't have a FC or FD in this case. In this case, FD that doesn't exist. So that means we cannot even talk about. So it's not the problem with the interval now. The problem with the point is not defined. So that means there is no real point to compare with. So that's the reason for that. So there are two reasons why there's no local minimum for this problem. Yeah. So that's the kind of idea why you cannot do that. So at the endpoints. So if it is closed, the part of the open interval is outside. If it's open, the point is not in there. So there are two reasons for that. Okay, and then so that's the first one, and then there's another one. So we normally you can say these local maximum are peaks or the valleys. So you can say these are. That's the kind of easy way to remember this one. So these are peaks or valleys. These are peaks or valleys of a function. So that's the kind of easy way to remember this one. So for example, so you can see, so the graph gonna take like shape like that. So then there's a local maximum and there's a local minimum. So there's a peak. So there's a max and there's the mean. Good. That's the easy way to remember this. The peaks and valleys. So as the third point, we're gonna notice this one. So let's say we have a local maximum. So you can see on one part of the function, you can see it is increasing. The other part is decreasing. That's for a maximum. First is increase, next is decrease. And if it is a local minimum, so what happened? First it is decreasing and then it is increasing. So that's happened for a minimum. Good. So yeah, so we can see on one side, we can do a real problem later. On one side, um, function, the function on one side, the function increases and on the other side function decreases. So this always happen when there's a local maximum and local minimum. So let's look at a few examples. Find the local maximum or minimum if any. So the first one, so we can look at the graph of y equal absolute value x function. So it has the shape like this. The graph of the absolute function. So you can see that if you look at the 0, you can see you can find an and this function is defined for negative infinity to positive infinity. So you can see around 0 you can make a small open interval. In that interval you can see 0 is the smallest value. If you look at this interval, so this is the corresponding part of the function. If you just look at this part of the function, and you can see at 0 you have the smallest value. So this is the minimum value. So that is the local minimum. So you can see uh, so if you say y equal fx, you can see f0, which is equal 0, is the local minimum. It's the local minimum. And you can see that's a valley. This is like a smallest point. So that's like a clear situation. Next one. Let's look at y equal negative x squared. So this is a parabola, inverted parabola. So the graph of this function looks like this. So it's a parabola but inverted. So it's gonna go like that. That's the graph. And again, this is very similar. So it's infinity to infinity. And you can see again, if you look at so you can see this point is the maximum value y, local maximum y. You can find an open interval around that point, and on that interval you can see, so that's the part of the graph. So if we do that, so this is a part of the graph that we are talking about, only this part. So if you look at this part, and you can see at 0 you have the maximum value. So you can see the local maximum or relative maximum, local maximum is 0. Okay, because you can find a small open interval that entirely inside the domain of the function, and on that interval you're going to see the maximum value at 0. Good. So let's do another one. How about y equal x cube, the cube function. So what happened for the cube function? You know the graph of this function. So this has the shape like this, but we can discuss more about this later. So that's the shape of the graph of the cube function. The problem is you can see that there are no any peaks or valleys. So even at 0, so you cannot see that, like for example, let's say if you suspect 0 is a maximum minimum, but the problem is you can see if you pick an open interval, in one part it is bigger, the other part is smaller. So for this function there are no local maximum minimum, local maximum or minimum for this function. So let's look at a function which has both maximum and minimum. Now let's look at this problem. So we have fx equal x squared. for x not equal to 0. So what is the shape of the graph? So you can see that for x equals 0, there is no point. So this is undefined. So the graph going to look like this. So you can see that this is almost the parabola, but the point at x equals 0 is removed. So for this one, and you can see since the point is not there, so there is no local minimum for this problem because there's no value that to compare with, because the value at 0 is not defined. So even if you take an open interval around that point, there is no value to compare. So there is no local minimum for this problem. So there is no local minimum. Local minimum. The reason is the point is removed. There's no local minimum. So next we're going to look at this one. And now let's look at this one. So fx equal x squared for x not equal to 0, 1 for x equal to 0. So these are what we normally call the piecewise functions. So we can discuss this later. So these are called piecewise functions. Piecewise functions. So the function is defined as pieces, like separately. Piecewise function. So that's like a different section that we discuss later. So the graph are gonna look like very similar. So this is what we get. So in this example, you can see that this one actually have a local maximum at the 0. So the reason is, so you can see that there is a local maximum. There is a local maximum at x equals 0. So this is an extreme situation because it's coming from the definition. So you can see if you consider an open interval, really small open interval around 0, and you can see that the value at 0, which is 1, is the largest value in this interval. So if you look at any other value in this interval, so you can see look at the corresponding function value. So this is the corresponding function part. You can see this part on this side and that's on the other side, and you can see that is smaller than 1. So you can see that f0 which is 1 is greater than or equal all the other values for all x in the open interval. So because of that, so there's a local maximum. There's a local maximum at x equal 0. So there are special cases that happen from the definition. So there's a local maximum around at 0 in this case. Okay, let's look at the next example. Find all the local maximum and local minimum, and also find where the function is increasing and decreasing. So we look at this graph. So in this graph, and you can see, so this is a point. So there's a point, this is -2, and this is a 1, and then this is 4. So you can see that at -2 and at 4, at x equal -2 and at x equal 4, there's a minimum value. The reason is, you can see if you consider a small open interval, then there's a minimum at -2. The same thing happens at 4. And on the other hand, if you look at 1, if you consider a small open interval around 1, and you can see at 1 there's a largest value, local maximum. So you can see so we're going to say the corresponding value. So there are local minimum. There are local minimum at, you can say x equal -2 and x equal 4. The minimum values are minimum values are 3 and 2 respectively. So that's one way to say it. And then also you can say the other one, you can say, let's say it like this. So there is a local maximum 6 at x equal 1. So you can see that's the other way to say it. Like in short, you can say what's the value and at what point. So there's a local maximum 6. The local maximum 6 at x equal 1. Now let's talk about the intervals. So you can say, so if you call the function is y equal fx, so you can say increasing on. So we're gonna write all the intervals with the union notation, and you can see it increases from it's a blue color for that. So you can see it increases from -2 to 1, and then also from 4 to infinity. That's where the function increases. Function goes up on those intervals. So we can write the answer is, so increasing on -2 to 1. We're going to say union 4 to infinity. We write them as open intervals, not closed intervals, because this can be useful when you do calculus. So we're going to use it like that. And you can see decreasing on the same arguments. You can see the function decreases from -infinity all the way up to -2, and then also from 1 to 4 the function. So what we do, we always consider the values x increases and see what happened to the values of y. We always go to the right, and when x increases, see what happened to the y. You can see y value goes down. The same thing, and here you can see when x increases, y goes down. Good. So you can say so it's decreasing on -infinity to -2, and the union you can say 1 to 4. So we write them as open intervals, not closed intervals. Okay, good. So let's look at another family example from trigonometry. So find all the local maximum and minimum of the sine graph. You will learn that these are shape of the sine function. These are what we normally call the periodic functions because the pattern repeats. It's called periodic functions. So you can see this in this one. There are infinitely many local. There's one local. This value is 1. So 1 is a local maximum, but that happen at many points. So system 1, so infinitely many points. So this is a local maximum. And then similarly, you can see there's a local minimum. There are infinitely many. So this is a -1, and this local minimum. Local minimum. This happens as infinitely many points. So we can discuss one last problem before we end this discussion. So let's look at this one. So again, the same question. Find the points. Find the points for which there is a local max or min. So we can look at this graph. So the constant function, so let's say it's open in one end and the close at the other end. So like that. So let's say this going from 1 to 5. So the question is what are local maximum and what are local minimum? So let's say this value is 2. So you can see that if you pick any point in this interval except the end points, and you can see like if you pick any point, like for example, let's say you're going to pick this point, and you can say clearly if you draw an open interval around that point, so that value, so if you call this function y equal fx, if you call this function y equal fx, and you can see that, so this is let's say c, and you can see that if c is less than or equal all the other points, because of the equal sign, you can see it satisfies this condition for any point in this interval. So the same thing happen like if you pick any other point, like let's say you're going to pick a point or is the same point like fc, you can also write fc greater than or equal fx for all the values inside that interval. So because of this reason, any point in the open interval from 1 to 5 are both local maximum and local minimum. So you can see any point, so this is a very special case, any point on the interval open interval 1 to 5 are local max and local min, both local maxima and local minimum. So they happen for both of them. It works for both. So these are special cases that are kind of confusing. Okay, so that's about the discussion about the local maximum and local minimum, and we're gonna discuss some extreme cases in a separate video because I don't want to confuse these ideas here. So let's look at the video like it's just extreme cases where we're gonna get some special results. And in another video, we can talk about what we call the absolute maximum and absolute minimum. Thank you.